Today we study graph algorithms. So we have already seen what are the graphs. We have already seen some trees. Trees are basically a particular type of graphs. So graphs are more generalized structures, and graphs are very important for computer science because it appears in many applications. Graphs basically captures the interconnectivity between objects. So how do you represent graphs inside the computers? There are two types of representation. So before I go to the representation of graphs, let me tell a little bit formally what is a graph. So a graph G is a tuple V cross E, where V is a set of vertices and E will be, so V is a set of vertices and E is a set of edges. So how do you define this vertices and edges? So V is a set of vertices. We can say, instead of vertices, we can say it's a set of elements. Elements can be anything. It can be integers. It can be some other objects. And E is basically a subset of V cross V. So this is the abstract notation of a graph. So you take a set of objects. I'm just drawing the graph. Okay, so this is just a drawing of the graph, but abstractly it does not have a drawing. So it's a set of vertices and edges are nothing but a pair of them. So how do we draw the pair? We just put some curves or some line segments joining those pairs. So this is an edge between, say, this is a V1 and V2. So V1 and V2 there is an edge. V1 and V3 there is an edge. It goes on like this. Now, so just let me tell you one of the applications in graphs. Suppose these nodes represent cities, and these are representing the roads between the cities. So we can represent this entire interconnection between the cities by the help of a graph. So there may be different problems. We may have to choose from one city, say V3 to say V2, what is the best way to go? What is the least distance over the roads we can traverse? So then if we represent this entire city interconnections using a graph, we can probably have an algorithm to find out what is the least connection, least weight connection or least path between V3 and V2. So now we have this abstract representation or mathematical definition of graphs. So now the question comes, how do you represent inside the computers this graph? Basically there are two representations. One representation is called matrix representation or adjacency matrix representations. So how do you represent this? So let me take an example. So suppose this is a graph. So this node is 1, 2, 3, 4 and 5. So this is a graph. This can be represented with a matrix like this. We have 5 nodes, so we take a 5 by 5 matrix. So 1, 2, 3, 4 and 5. 1, 2, 3, 4 and 5. Now suppose this is the matrix A. We mark Aij as 1 if there is an edge between I and j. So in this case, how do you represent? We assume that all the diagonals are zeros basically. I'll tell you why is it so later. Let's not worry about diagonals. Now let us see. For 1, so this is the 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So we have an edge between 1 and 2. So we should go from A1, 2 should be 1. So this is 1. Then A1, 3 there is no edge. We represent it with 0. A1, 4 has an edge, so that should be 1. A1, 5 does not have any edge, so that is 0. Similarly, let us see A21 has an edge, so that is 1. A22 we don't do anything because that is the diagonal element. A23 has an edge, A24 does not have it, A25 does not have it. A31 does not have any edge, A32 has an edge, A33 we don't care, A34 has an edge, A35 does not have, A41 has an edge, A42Z does not have any edge, A43 has an edge, A45 does not has an edge, A51 does not have any edge, A52, A53, A54 has an edge, and that's it. So this will be matrix representation of this particular graph. Okay. So this representation is quite simple. Suppose you want to know whether there is an edge between I and j, what you can check whether that particular entry in the matrix Aij, whether that is 1 or not. If it is 1, there is an edge. If there is 0, it does not have any edge. Particularly the diagonal elements represent Aii. What does it mean? Whether there is an edge between from I to I. That is, if there is a self loop, so this is called a self loop, whether there is an edge from 2 to itself, and we generally disallow these self loops. In our entire study, we will, until otherwise we specify this, we will assume there is no self loop, and that is why all the diagonal elements I have represented with 0. Now this graph, you can see all the edges, I did not put any direction on the edges. So this graph is an undirected edge, undirected graph. Suppose we put a direction on each edge like this, then this graph becomes a directed graph. Which, what does it mean? I have an edge from 2 to 1 now, but I don't have an edge from 1 to 2. Again, this directed graph can be represented using the adjacency matrix. What do we do in that case? In that case, we will have an edge from 2 to 1. So 2 to 1 will be 1, but 1 to 2 will be 0. This entry will be 0 now. Previously, both 1 to 2 and 2 1 were 1, but this time it is not the case. So in an undirected graph, for an undirected graph, this matrix is symmetric. So adjacency matrix is symmetric. It has to be, because if Aij there is an edge, Aji also has an edge. But for directed graph, this is not true. So directed graph not symmetric. All right. Now there is another version of the graphs which are called the weighted graphs. What are those weights? So in this case, edges have weights on them, some values. So for example, the previous graph, let me redraw it again. So in this case, say this is 1, 2, 3, 4, 5, and each edge, say this is has 0.7, this is 1.2, this is 0.5, this is 3.1, this is 2.0. And this can be now represented again using the 5 by 5 matrix, 1, 2, 3, 4, and 5, 1, 2, 3, 4, and 5. And in this case, the representation will be not 1 and 0. If there is an edge between Aij, then the entry Aij will have the weight for that edge. And if there is no edge between Aij, we represent it with 0. So this particular weighted graph will be represented like this, 0.7. You can verify later. Now there is a difficulty. You can see some of the edge weights may be 0. So in that case, this 0 will be confused whether there is an edge between the two nodes or there is an edge with weight 0. So that actually one has to resolve it from application to application. So I am assuming there is no edge weight for the time being, which is 0. So this is 0.5, 0, 0.7, 0, 1.2, 0, 0, 0, 1.2, 0, 3.1, 0, 0.5, 0, 3.1, 0, 2.0, 0, 0, 0, 2.0, 0. So in some applications, if the edge weights are 0, in that case probably you should represent this particular 0 with some high value, say infinity, some infinity value here. So all these 0 you can represent to the infinity, which represents that there is no edge, or basically there is an edge with an infinite weight, very large weight. Now, this particular matrix representation is quite good, as I have already told you, when edge weights, when you want to index some particular edge very quickly, whether you want to know whether there is an edge between A, I, J. But the bad part or disadvantage of this adjacency representation, disadvantage of matrix representation is that it takes too much of space. If there is a graph which has n vertices graph, one can easily verify it will take n square space matrix, because you will need basically n cross n matrix, and that will require how much space totally? Definitely omega of n square. So this matrix representation takes always theta n square space, no matter how the graph is. Suppose I have a graph which is very sparse, say I have this graph. Now this is a graph. We have 1, 2, 3, 4, 5, 6 vertices, but there is only a single edge. But to represent this graph, you will require 6 by 6 matrix. Most of the entries will be 0. So this is a very sparse graph where this number of edges is very less, but the representation is still taking order of n square or theta of n square. So that is not very good. So to overcome this, we have another data structure to represent graph, which is called the adjacency list. So in adjacency list, it consists of a linear array, we call V. V is an array of vertices, and a linked list of neighbors. Neighbors means, suppose V is an array, so ith vertex will be represented by the entry at Vi. Now Vi will point to a linked list which will have all the neighbors of the vertex I. That is, all the vertices which are adjacent to the vertex I through an edge. So let me see. Suppose this is the graph. Again, we take the same graph. So 1, 2, 3, 4, and 5. Now this will be represented like this in this data structure. So we will have an array V of 5 nodes or 5 entries, 1, 2, 3, 4, and 5. Each one, say V1. V1 will be pointing to all its neighbors. So 2 and 4 are its neighbor. So it will be pointing to say 2, another 4. Similarly, V2 will have a linked list structure. It will point to 3, it will point to. Then V3 will point to 2, and this will point to 4. V4 will point to 1, this will point to 3, and then this will point to 5. Similarly, V5 will point to only the single one, which is 4. So this will be the representation of this graph with adjacency list data structure. Now one can verify what is the size of this data structure now. It is nothing but first the array size, which is of order of n. So this is the order n size for array V plus the size of all these linked lists. Now, what is the sum of the size of all these linked lists? It is nothing but the sum of the degrees of each vertex. So let us see what is the sum of the degrees of all vertices in a graph. So suppose di is the degree of a vertex in the graph. What do we mean by degree? It is nothing but the total number of neighbors or total number of vertices adjacent to the vertex I. Now sum of di over all I, it can be proved that it is exactly equal to 2m, where m is the number of edges. This is the proof is very simple actually. You take each edge, you can count, you can look at this sum a little bit differently. You are counting all degrees over all the vertices. Now you can look at this count as if each edge is contributing 2 vertices, that is the 2 endpoints of it, to this count. So each edge is contributing a count of 2. That's why this must be equal to 2n. So this is the sum of the degrees, and this must be equal to the sum of the all the linked lists represented in the adjacency linked list structure. So total size now becomes nothing but order m plus n. Now here is a point. Is it better than matrix multiplication? Matrix representation? Yes, definitely. Suppose your m is much smaller than n. In that case, this will give you order n complexity space. But in the matrix representation, it is always order n square. So suppose m is say almost constant 1 or 2, this will give you order n. But in even m is 1 or 2, matrix representation data structure will always give you order n square. But mind that when m is equal to n square, order of n square, it can be, suppose you take the complete graph, that means every vertex is connected to every other vertex. That graph will have how many edges? N choose 2, which is order of n square. In that case, this also will be of the order of n square, this data structure. But there are most of the times when m is much less than n, this will be much smaller. So this is much better in terms of the space. But the disadvantage of this data structure is, suppose I want to know whether there is an edge between aij, then one has to do a search in the linked list. You cannot just see the index immediately in the data structure and check whether there is an edge between the two nodes I and j. Here you have to go through the linked list of ai and check whether j is present there. So that will take some time in this case. Now we know how to represent the data structures to have a graph within the computers. Now let me be a little bit precise about the structures of the vertices and edges inside the graph, because all the algorithms will refer to this structure. I am not using any particular type of language here, but the way I will be representing is mostly like Pascal, but it should be clear to you what do we mean. You can write this one in C or C++ or any other language. So this is our type declaration. What we do in type declaration, we declare the vertex. How do we represent vertex now? It's a record. So in C it will be a structure which will have 2 integers. I'll tell you later where these are used. And pi is an index. Basically index is nothing but an integer. And there is another field called adjacency list, which is a pointer to another structure called edge, which I am going to define. So this is the vertex structure. So how do you define now edge? age is a record again, where v is an index. Basically, this index is again an integer which will represent a vertex. Vertices are represented with an integer. And next is again a pointer, is a self pointer to the structure itself, age, and that is n. And then we declare the array, which I am calling it as adjacency structure. This is nothing but an array of 1 to n of vertex. Now we can declare as a variable, say v is the variable which is of type adjacency structure. So v is an array of the type adjacency structure. Adjacency structure, I have defined it that each element is of the type of vertex, and vertex is defined like this. I will explain later in our algorithm what are these d, f, pi and adj. So if you go back and check the adjacency structure here in this, you can see v is an array and this adj is nothing but a pointer to the linked list. So here like this, so adjacency structure will be nothing but a pointer to this age, and age will have what? It will have an index of the type vertex, or sorry, it will have the index for the vertex, and then it has a pointer again. That's what it is here. You can check. If you go to age, v is an index, it has two parts, and next is nothing but a pointer to a similar structure which is called age. Now with these structures in mind, we will explain one very important algorithm on graphs which is called the depth first search. Probably you have seen this one in tree structures. When you have done trees, then probably you know what do we mean by depth first search in a tree. So now we will explain how to traverse the nodes of a graph in a systematic manner. And actually this particular type of search can be used for other algorithms or for finding several properties of the graph. So depth first search, what it does, given a node, it starts at a node of a graph and it goes on traversing all the nodes it can get as deep as possible in the graph. So suppose from node V it starts and it sees that the next one V1 is its neighbor, it goes and search this, traverse this, then before it goes to the neighbors of V again, it goes to the neighbors of V1 itself. So V2, from V2 it can go to V3, and suppose V2 does not have any more neighbor, it will come back to V2, and probably it will start from another neighbor of V2, it may go down again. So why is it called depth first? Because before we traverse all the neighbors of V, we are going deep down the graph. That's why it is called the depth first. Actually there is another type of search which is called the breadth first, in which case you will traverse V1, and before you go to the neighbor of V1 you will traverse all the neighbors of V first. So it's like this. In that case the search will proceed like this. First you complete this level, then this level, like this, but in this case we are traversing in the deep down the graph. So let me write down first this algorithm, then I will explain what are the steps. For I is equal to 1 to n, do vi dot d is equal to 0, end for, and time is equal to 0. I will explain all these terms later. For again I is equal to 1 to n, do if vi dot d equal to 0, then vi dot pi is equal to nil, then visit I is a call, end if, end for. So now let me write down. before I write down this, so you can see we are calling a procedure called visit. Before I write down the visit, let me just explain what we are trying to do here. So we have been given a graph. First, we are initializing each vertex the D field. You remember in the data structure we had a D and F field. Basically, those two are representing some sort of timestamps. The first time we visit a vertex, we initialize its D value, and when we finish visiting that vertex, we compute or we put its F value. So initially, all the D values are 0 because we have not visited them, and we maintain a variable called time. So this time variable will give the timestamps to each vertex when we have visited that vertex, because these fields, when we have visited this vertex and when we have completed this vertex, will give some more information on the graph. We will see it later. So initially we timestamps all the vertices, n vertices, with vi dot d is equal to 0, and time is initialized as 0. Then we are checking whether the timestamp is equal to 0. That means if a vertex is not visited yet, then we go and visit that vertex. Why is it important? We will see that visit routine will be a recursive routine, because as I have drawn, suppose we start from this vertex I, say visit I, this will give a recursive call to visit its neighbor, this will give another recursive call to visit its neighbor, it will go on. Now in this traversal, some part of the graph may be visited, but some of the other parts of the graph may not be visited. So this visit will complete and come back, and then we will check whether we have visited all the vertices in this recursive manner or not. If some of the vertices are not yet visited, then we go and give another recursive call on those vertices. That's why this loop is for. So this is going down the array V and checking whether something is visited or not. If a vertex vi dot d is equal to 0, that means it has not been visited yet. We will go and start a new visit. And let me tell a little bit about what is this pi field doing. Pi field is basically giving the information for the vertex from which this particular vertex has been visited. So this, suppose I have this vertex say v1 and we are visiting v2, we gave the visit I or visit 2 call from visit 1. In that case, this pi field of 2 will have the information that it has been visited from 1. And whenever we start a new visit, its pi field is null or nil pointer. So suppose we have visited v2 and we have completed this entire visit and still some more is left, then we start, suppose, the new visit from this vertex, then this vertex say x will have its pi field null. Basically it indicates that we are starting a new visit from this vertex, and probably this will complete and visit some more vertex, say this is say y, and in that case if y is visited from x, y's pi field will be nothing but the value for the index of x. So basically when we complete all the visit, if we see each vertex pi field, we can go back and reconstruct this path during our depth first traversal of the tree. Now let me write down the recursive procedure, which is the visit procedure. So here procedure visit I. So time, now since we are visiting this, we have to increase the time. Time is equal to time plus 1. Now you initialize your its d field, which is equal to time, because at this moment you are visiting this. You get the first node in its linked list, which is obtained by its adjacency field. You remember we had vi is nothing but a pointer to an edge. Sorry, vi is nothing but a vertex structure, and vertex structure has a field called adjacency list or adj, which will be pointing to its linked list. While now we visit or we check all the nodes in its linked list whether something has been visited or not. If it is not visited, we will give a recursive call. T is not nil do if, here is the check, if v t dot v dot d equal to 0. Don't get confused here. What is v dot v t dot v. T is a pointer to an edge structure, and t dot v will give you the index for that vertex. If you go back to the structure, you will realize. So we are basically, it is checking whether this vertex in the linked list, its d value is 0, whether it has been visited or not. If it is not visited, if it is 0, then you first visit it. So p v dot v, so this is small v, basically this is small v, this is a big V. Vt dot v dot pi fill is initialized here as I, because you are visiting this vertex v from the vertex I. So this, its pi field is initialized to I, and you give a recursive call visit t dot v, and this is the end if, and then you basically traverse the linked list t dot next is the end while, and then when you come back, basically when you have completed its linked list, you update the time, and you have basically finished visiting I, then you put its f value, vi dot f is equal to time. So in this while loop, we are going through the linked list of I and checking whether any of its node in the linked list is not visited. If it is not visited, its pi fill is initialized. Then you visit that node. It's a recursive call. And then when this recursive call comes back, then you go to the next node, t is equal to t dot next in the linked list. When this while loop is done, that is you have checked all the nodes in its linked list of I, you have basically completed the visit of I, then you increase the time is equal to time plus 1, and then you put the f field of I with that time. Basically you have finished at that time visiting I. So this is the recursive visit procedure. Now let me take an example and show you how d and f values of the nodes are initialized by this algorithm. So let me just take an example. So I will be assuming a directed graph, all right. So let me just draw one directed graph. Here is just an example. Remember, we can use the same data structure for the undirected graph. By slightly changing it, we can use it for directed graph. Only thing, we have to represent a direction for each edge. Now suppose this is the graph, and we start our visits say from this node. So I will be representing the starting time and finish time like this, d slash f. Whatever number here, it will be the starting time, whatever number here is the finish time. So this node has started at time is equal to 1. Now this has given, suppose it has two neighbors. Now suppose it goes to this one first, so it goes here and it visits this node using this particular edge, and its timestamp is 2 now. Now again from this one there will be a recursive call to visit, and probably it will go to this node. So this will be, this timestamp is 3, is incremented by 3. Then probably this will go and visit the next node which is not yet visited, whose timestamp is 4 initialized. Then you can check this particular node does not have any more neighbor which is not visited. It has one neighbor like this one. It can go to this node, but if it goes and check, its d value is already 2, it's not 0. So it will not go and visit this node. So this while loop for this node will be ended, and this visit for this node will be done. So in that case, its finish time will be recorded as 5. Then this is done, the recursive call will go back to this particular node, and it will check whether this particular node is done or not, and in this case this particular node is also done because it does not have any more neighbor which is not visited. So its finish time will be recorded as 6. Now this recursive call will go back here. It will check whether some more nodes has to be visited in its linked list, because it has only checked one and there is one which is not yet visited in its linked list. So it will go and give a recursive call for this one. So this will be now visited, and this start time will be 7. Now for this node, it will see its neighbors are visited. Yes, this is already visited, so it will be done. Its finish time will be recorded as 8. Recursive call will go back here, and this time this particular node is already visited, has been finished because all its neighbor are visited. This is done, so this finish time will be 9. The recursive call will go back here, and it will check whether its neighbors are visited. Yes, both of its neighbors are visited. In that case, this is also done, and its finish time will be recorded as 10. Now we started the visit call from this node, and the visit call has come back and it's done already. And this particular visit call has visited these nodes, but you can check that all these 3 nodes are not yet visited, because those 3 nodes could not be reached from this particular node. So in that case, what will happen, if you remember in our this particular initial for loop, like here, this particular for loop will take over, and it will initiate another visit call for this one of these 3 nodes here. So suppose it initiates the new visit call from here. So the timestamps now will be 11 because the last finish time was 10. Then this will probably visit this node now. So this timestamps will be 12. All its neighbors are visited, so this will be done. So this finish time is 13. The recursive call comes back here, and this will check whether any more neighbor. Yes, there is a neighbor, so this will go via this edge, and this will be say 14. Its finish time will be 15, and this will go back, and this finish time will be 16, and this call will be ended. And the for loop, the first for loop, will check and see that all nodes are visited. Vi.d is not 0 for all the nodes, so this will be done. So this is the entire depth first search for this particular example. Now once we have done this, so you can see the pi fields will record these edges. The edges I have indicated with curly lines. All the other edges will not be recorded. So we can redraw this graph using the depth first search a little bit differently. So let me redraw this graph now. Start from the started node 1 by 0, because this node start time is 1, finish time is 10, 1 by 10. Then we have visited the next one using, so this will be 2 by 9, this node. Then from this one we gave 2 recursive call. So this will be 3 by 6, and we gave another recursive call which is 7 by 8. So these 2. From 3 by 6 we gave a recursive call which is 4 by 5. From 7 by 8 we did not give any recursive call. This particular call ended with these visits. Then we gave a new call of visit 11 by 16. There is this node. Then we gave another recursive call from this node to 12 by 13, and another node to 14 by 15. Right now there are some more edges which are not indicated yet, so I am going to draw them. So there is an edge like this, because between 1 by 10 and 7 by 15, 7 by 8 there is an edge like this. So that's what I have drawn here. Then there is an edge from 4 by 5 to 2 by 9 in the original graph I have drawn. From 7 by 8 to this one I have drawn. Now from this one to this there is an edge. This one to this there is an edge. There is an edge like this. There is an edge like this. Now we can categorize all the graph edges into 3 groups. Actually 4 groups. One we are called the tree edges. Then we call forward edges. then we call backward edges, then we call cross edges. I'll tell you what are the definitions. First, the tree edges are the edges which have been visited by the DFS, the dress for search, the ones which I have indicated with curly lines. So these are called the tree edges. Now those edges which are going in the forward direction, that means whose starting value is more, like if I have an edge from I to j where j has a starting value more than the starting value of I, in that case that edge will be called the forward edge. So this is a forward edge. Similarly, I don't have any more forward edge here. What is the backward edge? Is just the opposite of forward edge. If I have an edge from I to j where j has a starting value less than I, in that case that is called the backward edge. So this is a backward edge. Do we have any more backward edge in this case? So here is a backward edge. There is no more backward edge in this case, and all the other edges are called the cross edges. See. So these are called the cross edge. So let me define a little bit more formally what is a backward edge and what is a forward edge, so that you are not confused. So first of all, tree edges. So tree edge, what is the definition? If ij is a tree edge, then vj dot pi equal to I. It must be that. So you can just check if it is tree edge, basically it must be visited through that edge. Then back edge or backward edge, what is the definition? Edges ij so that j is an ancestor. So this time we are going giving the definition more formally and differently. Ancestor of I, and forward edge is non-tree edges ij such that j is a descendant of I, and rest are cross edges. So let me go back. So we are going. I have given another definition now for tree edges, forward edges, backward edges, because to give the definition using the starting time and finishing time, we have to tell a little bit more than what I just said. It was not completely correct. So let me give you another definition. First of all, using the edges of the DFS, we can define a spanning for a tree or a forest in this case. If you just draw the tree edges, you can see it's a tree, it's a forest now, like all those curly ones. Now in this forest, I can define what is an ancestor of a node, what is a descendant of a node. So a forward edge is, but ij is a forward edge if j is a descendant of I. So in this case, you can reach this node from this node. So this is a descendant of this node in this particular tree. And backward edge is ij is a backward edge if j is an ancestor of I. In this case, this is the backward edge. This is the backward edge. Now all the other edges are cross edges. You can see this edge ij does not have any relation of ancestor or descendant relationship. And we will see later how this backwards edge and forward edge can be determined using the D and F value in the next class. And we will also see in the unrelated graph there cannot be any cross edges, only backward and only forward edges. Okay, so that much today. In the next class we will continue on this DFS for unrelated graph and probably BFS on the graphs.